Welcome to lecture 31. In this lecture, I will talk about the Dirac equation. In lecture 23, we calculated the classical equations of motion for a scalar field. These were given as the derivative of the Lagrangian density L, and if we were considering a real non-interacting scalar field with the Lagrangian density that's given in this equation here, these classical equations of motions become box phi minus m squared phi 0, which is known as the Klein-Gordon equation. In this lecture, we want to study a relativistic wave equation, not for scalar fields, but for fermionic fields. To get started, recall that we do have a wave equation for fermionic fields, which is the Schrödinger equation. For a free particle, the Schrödinger equation is given as the equation shown in this equation 31.3. It's the I times the time derivative of psi is minus 1 over 2m times the space derivative squared acting on psi. Unfortunately, the fact that we have a single time derivative on the left and two space derivatives on the right immediately make it clear that this Schrödinger equation is not relativistically invariant. And for proper relativistic quantum field theory, we cannot use the Schrödinger equation as a building block. We need to generalize the Schrödinger equation to a relativistic field equation. In the free Schrödinger equation, the Hamiltonian is just p squared over 2m, where p is the momentum operator. This looks very much like an expansion of the relativistic energy, where the energy is given as the square root of p squared plus m squared. And if we expand this for small momentum p, we get m plus p squared over 2m plus and so on and so forth. The m term is just a constant. This wouldn't appear in our Hamiltonian. And then we have the p squared over 2m, which is the term that we find in the Schrödinger equation. So we are tempted to write down a wave equation such as this: I dt psi is equal to square root of p squared plus m squared acting on psi. But this equation also has some problems. The fact that we have a square root in the operator in here means that it is non-local. And also the fact that the time and space derivatives don't appear symmetrically mean that it is also not relativistically invariant. Clearly, this wave equation 31.5 cannot be the correct relativistic spin 1/2 wave equation. However, equation 31.5 does have an interesting property. If we iterate the solution, meaning that we sort of take the operators on both sides twice, we get on the left-hand side minus time derivative squared on psi, and on the right-hand side we get p squared psi plus m squared psi, which we can bring into the left-hand side again to find this equation here. If we plug in the form of the momentum operator, we find that iterating 31.5 just gives us back an equation that is nothing else but the Klein-Gordon equation. So the square of the wrong wave equation 31.5 is in fact a proper relativistic wave equation. Dirac's trick was to recognize that we could start from the Klein-Gordon equation and would have to take a square root out of the Klein-Gordon equation to get the wave equation that we need. However, since 31.5 was the wrong square root, we needed to take the correct square root out of the Klein-Gordon equation. He wanted to write down a wave equation that was linear in derivatives. So he started or made an ansatz for the wave equation that now bears his name, the Dirac equation, in which we have I dt psi on the left-hand side, and the right-hand side we have the Hamiltonian acting on psi. And he made the ansatz that the Hamiltonian consists of two terms. One is the derivative operator nabla, and the other one is a constant term that is proportional to the mass, where these two terms, since we don't know them yet, come with two constants, alpha, that's multiplying the derivative operator, and beta. Obviously, we wanted to get the Klein-Gordon equation if we iterate this Dirac equation. So if we iterate the left-hand side, we get minus dt squared psi, and then the right-hand side, we get this operator acting on psi twice. We can expand these individual terms and find that it is given as alpha I alpha j times di dj minus a linear term in di and a term that's just the mass squared. So if you have ordinary numbers alpha and beta, we will get a non-vanishing linear term here unless these numbers are 0, in which case we don't get a Klein-Gordon equation. So for ordinary numbers alpha and beta, this is not a Klein-Gordon equation. However, Dirac realized that it can be the Klein-Gordon equation if we generalize alpha and beta to be not numbers but matrices. In particular, if they are matrices that fulfill the following anti-commutation relations, that alpha I alpha j is twice delta ij times unity, alpha anti-commutes with beta, and beta square is just 1. If you plug this in the equation 13.1.8, you find that indeed the Klein-Gordon equation is recovered from the ansatz for the Dirac equation. In modern notation, we usually define the following Dirac matrices, which we denote as gamma mu. And these are equal to the matrices alpha and beta in the following form. So gamma 0 is beta, and gamma I is beta times the individual alpha matrices. The Dirac matrices then fulfill the anti-commutation relations. Anti-commutator gamma nu is minus twice metric g mu nu times unity. And they have properties under Hermitian conjugation that can be worked out. In particular, the Hermitian conjugate of gamma 0 gives back gamma 0, and the Hermitian conjugate of gamma I just gives minus gamma I. So gamma 0 is Hermitian, whereas the space-like gamma matrices are anti-Hermitian. Also, we can use this last result here and use the Clifford algebra to show that the Hermitian conjugation of any Dirac matrix gamma mu can always be written as the following product with gamma 0, namely gamma 0, gamma mu, gamma 0. Using the gamma matrices, the Dirac equation then is given in the following form. It's I d mu gamma mu minus m acting on psi is 0. It fulfills the following property. If we act on this Dirac equation with the conjugate, we find that we have I d mu gamma mu plus m, I d mu gamma mu minus m is equal to minus d nu gamma mu minus m squared psi. And if we then use the Dirac algebra, so the Clifford algebra for the gamma matrices, we can replace this by minus g mu nu times unity, so that the first part here just becomes the box operator. We find that this equation here is nothing else but the Klein-Gordon equation. However, since gamma mu is a matrix, in order for this equation to make any sense, the field psi must have multiple components. This is unlike the scalar field phi that we have treated so far, and we call psi now a Spinor field. There are different choices for the gamma matrices that all fulfill the Clifford algebra. These different choices are called representations. In lower dimensions, in particular in 2 dimensions, we can just choose from the Pauli matrices, sigma I, to find representations of the Clifford algebra in 2 dimensions. In 3+1 dimensions, we can also use the Pauli matrices and string them together in 4x4 matrices. In particular, we have the Dirac representation as one particular representation fulfilling the Clifford algebra in 4 dimensions. Here, gamma naught is defined as the following 4x4 matrix. It's block matrix with a unity matrix in the upper left, 2x2, then zeros in the off diagonal blocks, and minus unity in 2 dimensions in the lower right-hand block. And the space-like gamma i's are represented in terms of the Pauli matrices sigma 1 to 3. Since gamma mu are 4x4 matrices in 3+1 dimensions, the Spinor field also has 4 components, and sometimes this Spinor index is denoted as a grid index alpha. So we sometimes write psi is equal to psi alpha. And in 4 dimensions, this corresponds to a 4-component spinor. Also, the combination d mu gamma mu often appears whenever we have to deal with Spinor's fields. And it's customary to introduce a shorthand notation for this combination. This is this derivative operator with a slash in it. It's pronounced slash d, and it just stands for d mu gamma mu. This is called the Dirac slash, and it can also be used for other contractions that gamma mu acts on some other quantity. For instance, we could have a slash, that's gamma mu a mu. Since the spinor psi is in general a 4-component complex object, we need to sort of employ Hermitian conjugation to make a real scalar object. For instance, we could want to write down something like psi bar psi dagger psi, where psi dagger is nothing else but the Hermitian conjugate. Then this quantity here is real and scalar. But because of the special role of this gamma matrix gamma 0, which was the matrix beta in Dirac's original notation, it is also customary to define the Dirac adjoint. This is denoted as psi bar and is given as psi dagger times the 0 gamma matrix gamma 0. And this notation will come into play whenever we have to deal with the Dirac field in the following lectures. And this concludes the lecture.